Have you ever just looked at the world and felt like it's teetering on this knife's edge between perfect, predictable order and just total chaos? Well, what if I told you that entire knife's edge could be described by a single, shockingly simple equation? Today, we're going to look at the formula that actually governs that descent into madness. So let me ask you a question. What in the world connects the steady rhythm of a leaky tap, the frantic, dangerous beat of a fibrillating heart, and the infinite, mind-bending complexity of a mathematical fractal? It sounds impossible, right? But believe it or not, they are all playing by the exact same rules. This is it, this one tiny little formula. It's called the logistic map, and it holds the secret to how perfectly simple, predictable systems can suddenly, and I mean suddenly, collapse into complete and utter chaos. And today, we're going to unlock it together. All right, so to really get our heads around how this works, we don't need a supercomputer or anything fancy. We just need, well, a bunch of rabbits. This is where it all starts. Okay, so here's the model. Super simple. X is just our current rabbit population. We'll represent it as a number between 0, for no rabbits, and 1, for the maximum possible population. And R, well, R is the fun part. That's the growth rate. Think of it like a dial we can turn up or down to control how fast these rabbits, make more rabbits. Let's try it. We'll set our growth rate R to a nice, moderate 2.6. And let's say we start with a population of 0.4. When we run the equation once, we find out the next year's population is 0.624. Okay, so it grew. But here's the key. What happens next? We take that new number, 0.624, and we plug it right back into the same equation. And we just keep doing that year after year after year. And after we run it over and over again, something kind of cool happens. The number just settles. It stabilizes right here at about 0.615. The population has reached this perfect, totally predictable balance. Kind of boring, right? Well, hold on, because this is where things start to get really weird. So what happens when we start cranking that R dial? When we push the growth rate just a little bit higher? This is where we leave that simple, boring order behind, and we step right into mind-bending chaos. You see, as long as our growth rate R stays below 3, everything is totally stable, predictable. The population always settles on one single number. But the very moment we push R just past 3, something snaps. The system just can't settle anymore. Instead, the population starts bouncing between two different values, year after year. And as we keep pushing R higher, the pattern just keeps going. Those two values split into a 4-year cycle. Then that splits into an 8-year cycle, then 16. These splits, they're called bifurcations, and they start coming faster and faster and faster, until finally, at an R value of about 3.57, everything just breaks. It's pure chaos. The population numbers never repeat. They just jump around, seemingly at random, forever. Now think about that for a second. This is the crucial point. We're using a perfectly deterministic equation. There's no randomness here at all, but the result looks completely and totally random. And if we plot every single possible outcome for every R value, we get this. This beautiful thing is the bifurcation diagram. It's literally a complete map of that entire journey, from simple order all the way to chaos. But what we don't realize yet is that this map is hiding an even bigger, crazier secret.
Okay, I need you to prepare to have your mind blown. Because this incredible pattern we just discovered, it turns out it has a very, very famous relative.
So on the left, that's our equation, our little rabbit model. On the right, that's the equation for the most famous fractal in the entire world, the Mandelbrot set. Now, they look different, for sure, but they share this deep, fundamental, almost unbelievable connection. Look closely at the Mandelbrot set, but turn it on its side. You see that thin line running right through the center of it? That's it. That's our bifurcation diagram. The journey from order to chaos we just mapped out with our rabbits is literally the backbone of the Mandelbrot set. Two completely different mathematical worlds, and one is literally hidden right inside the other. And if that isn't strange enough for you, let's talk about the speed at which all this chaos arrives. Because as it turns out, the universe seems to have a speed limit for chaos, and it is governed by a secret number. This is it, 4.669. It's called the Feigenbaum constant. It's not pi, it's not the golden ratio, it's something else entirely. It's a fundamental constant of nature that was discovered hiding inside this very process. So what is it? It's a ratio. If you look at our diagram and you measure the width of one of those little forks, and then you measure the width of the next, smaller fork, the ratio between them always converges on 4.669. It's like the universe's speed limit for accelerating into chaos. Now here's what's truly spooky about this number. It's universality. I mean, it doesn't just work for our rabbit equation. It works for any similar equation that has a simple peak, a single hump. You could use sine waves, you could use tons of other formulas, and this exact same number, 4.669, will pop out every single time. It seems to be woven into the very fabric of reality. And the craziest part? Nobody knows why. Look, this isn't just some abstract math idea. This pattern, this road to chaos, is literally happening all around you right now. For example, in actual experiments, scientists heated up some mercury in a box and measured the temperature. And as they turned up the heat, guess what happened? The temperature spikes went from a single rhythm to a 2-beat rhythm, then a 4-beat. They were exactly following our period doubling route to chaos, right before the fluid erupted into full-on turbulence. And remember our rabbits? Well, it gets even more real. Scientists found that on the path to cardiac fibrillation, which is a chaotic and lethal heart rhythm, a real rabbit's heart also follows the period doubling route. They even use this knowledge to figure out how to apply perfectly timed electrical shocks to pull the heart out of chaos and back into a stable, orderly beat. And you can literally see this for yourself. Go to a sink, turn the tap just enough so you get a steady drip, drip, drip. Now increase the flow just a tiny bit. You'll hear it shift to a 2-beat rhythm. Drip, 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 drip. A little more, and it becomes a mess. Pure chaos. That's it. Order to chaos. Right there in your kitchen. The biologist Robert May argued way back in 1976 that this concept is so fundamental it should be taught to everyone, because it gives you a whole new kind of intuition for the world, a way of seeing how the absolute simplest rules can blossom into the most complex, unpredictable, and honestly beautiful behaviors imaginable. So the big lesson here is that complexity isn't always complicated. Sometimes it's born from the simplest little rules, just repeated over and over again, which of course leaves us with one final nagging question. If a pattern this profound was hiding in an equation this simple, what other earth-shattering secrets are we all overlooking every single day?